Hello, my dear students. Today we shall discuss the important concepts of ideals, that is, principal ideal. An ideal I is said to be a principal ideal if it is generated by single element. An ideal I, we denote it by the notation I. An ideal I is said to be a principal ideal if it is generated by single element. Now the question arises in our mind, what is the meaning of generated? Generated means from single element we have to get many elements. It's same as cyclic group. In the cyclic group, we used to see the integral power of an element. For example, a cyclic group generated by 2 means what? 2, 2 square, 2 cube, 2 to the power 4 and so on. Here it is not like that. Here we see integral multiple time. I means ideal. An ideal generated by an element A. For some A belongs to I. Generated by A can be written as or can be represented by AR or RA, provided R belongs to what? R. Since we observe AR or RA, that indicates this is not simply a ring, but it is a commutative ring. Okay, I hope you got it. Since we observe AR or RA, we call this ring as commutative ring. That means to define the definition of principal ideal, we should have what? Commutative ring. We know that the set of integers is a commutative ring. Let us take an example. An ideal generated by 5. An ideal generated by 5. That means we have to take the multiples of 5. We denote it by 5n for all n belongs to z, because set of integer is a commutative ring. Okay, multiples of 5. Multiples of 5 means 0, plus or minus 5, plus or minus 10, plus or minus 15 and so on. So this is the definition of what? Principal ideal. Now I will define one more definition, that is principal ideal ring. Principal ideal ring means a commutative ring with unity and without zero divisors. Let me repeat, a commutative ring with unity and without zero divisors is same as the definition of what? Integral domain. Is said to be principal ideal ring if every ideal in I is a principal ideal. That means to define a principal ideal ring, we should have what? Principal ideal. Principal ideal means it should have a generator. Now I will define one more important concept of an ideal, that is maximal ideal. Maximal ideal. To define a maximal ideal, we need a proper ideal. Let me recall the definition of, the types of ideal. There are two types of ideals, namely improper ideal and proper ideal. Is same as subring. In the subring also we observe improper subring and proper subring. Okay. To define a maximal ideal, we need a proper ideal. Proper ideal I denote it by M. Proper ideal means the ideal M is not equal to ring R. That means both are distinct. Whenever M is not equal to R, that indicates it is a proper ideal. That means a proper ideal of a ring R is said to be a maximal ideal of R. Listen to my words carefully. There exists another ideal. Let me denote it by N, such that M is contained in N and N is contained in R. M is contained in N and N is contained in R. Then either N equal to R or N equal to M. This is the definition of maximal ideal. Maximal, let me recall the definition one more time because the important concept. Any ideal, not any ideal, we should have to take a proper ideal. A proper ideal is said to be maximal if there exists another ideal, say N, such that M is contained in N and N is contained in R, then either N equal to R or N equal to M. Let me rewrite the important points of this definition. M is not equal to R. That means proper. M should be a proper ideal. Second condition, M is contained in N and N is contained in R. Then N equal to R, N equal to M. Either N equal to R or N equal to M. Let me define this definition in another way. Let me take a ring, the red circle, the circle, the first one, the outer circle. I call the outer circle as a ring and the inner circle as the innermost. The innermost circle is said to be the proper ideal. Outer circle is ring and inner circle is proper ideal. In between the inner and outer, we have the dotted circle and I'll call that circle, I will call that one as N. N means any ideal. What is definitely what we observe here? This M is not equal to R. Clear? The second one, this M is contained. This M is contained in N. This M is contained in, this is M, this is N. M is contained in N and N is contained in what? R. Definitely what we observe here, this N either same as M or is same as R. This is the definition of maximal ideal. That means to define a maximal ideal, we need a proper ideal M and another ordinary or any ideal N satisfying these two conditions. The first one is what? M is not equal to R. The second condition is what? M is contained in N and N is contained in R. Then N equal to R or N equal to M. One more concept, that is prime ideal. To define a prime ideal, again we need an ideal. Okay? Let R be, let me define the concept prime ideal. Let R be a commutative ring. An ideal P, I will denote it by the capital letter, that is P. An ideal P of ring R is said to be a prime ideal of ring R if it satisfies two conditions. The first condition is what? P is not equal to R. Whenever we write P not equal to R or any notation not equal to R, that indicates what? That indicates it may be M or P. Here it is P is a proper ideal. The second condition, If the product of two elements belongs to P, then either first element belongs to P or second element belongs to P. Then we call this one as prime ideal. That means to define a prime ideal, we need a commutative ring. Okay, an ideal P is said to be a prime ideal if it satisfies these two conditions. The first condition is what? That P should be a proper ideal. That means MP not equal to R. The second condition, AB belongs to P, implies either AA belongs to P or B belongs to P. Let me note down some important results related to the definitions. Every maximal ideal is a prime ideal, but converse need not be true. That means if the ideal is maximal, that means it is prime. Every maximal ideal is a prime ideal, but the converse is not true. That means the prime ideal need not be maximal ideal. One more result, ZP means what? Integer modulo P is a field if P is a prime. That means if it is a prime, then the integer modulo P is a field. We know that, and we know that every field is an integral domain. One more result, every field has two ideals. I'll take examples so that you will understand the first result, second, third and fourth. Okay, I'll take examples related to these results. Now, some important results I want to recall here. A divides B can be written as A divides B can be written as B equal to AP for some P belongs to set of integers. For example, is 2 divides 4. Is 2 divides 4. Yes, answer is yes, because B, in place of B 4, in place of A 2, in place of P, what I have to take? I have to take an integer. Here I will take that P as 2. So 2 into 2 is 4. That means 2 divides 4. Next example, is 2 divides 6. Again the answer is yes, because 6 is equal to, in place of B we have 6. 6 equal to 2. A is 2 into 3. 3 is an integer. Is 2 divides 5? Answer is no, because denominator, that is 5, is equal to 2 into 5 by 2, because if I cancel these two, 2 into 2 get cancelled, we get only 5, but 5 by 2 is not an integer. 5 by 2 is not an integer. Let me take one more example. Is 2 divides 7? Again the answer is no, because 2 by 7 can be written as, 2 divides 7 can be written as 7 equal to, in place of B, 7 is equal to 2 into 7 by 2, but 7 by 2 is not an integer. Okay, now another result, generated by A means multiple of A, that is An, or you may write Na, because the commutative law holds good. Generated by A is same as writing A divides N. For example, 2 divides 4 can be written as generated by 2, that is 2 into 2 is what? 4. Keeping these two results in mind, I'll take few examples. Find the maximal ideals and prime ideals with the following. The first one is Z4, Z8, Z10, Z12, Z36, Z49, 23 and Z101. That means integer modulo 4, integer modulo 8 and so on. Let me take the first example. Integer modulo 4. It has only 4 elements. Integer modulo 4 has only 4 elements. First element is this. First element is 0. Second element is 1. Third element is 2. And next element, the last element is 3. Okay. Now, let me find out the ideals of Z4. Ideals of what? Z4. The first ideal I denoted by I1. 1 divides 4. 1 divides 4 means generated by 1. Generated by 1 means what? Generated by 1. 0, 1, 2 and what? 0, 1, 2, 3. And these are the elements of what? Z4. Now generated by sorry. And we call this one as proper ideal. I2, next ideal I denoted by I2. 2 divides 4. 2 divides 4 means generated by 2. Generated by 2 means multiples of 2. Multiples of 2 means what? 0 into 2, 0. 1 into 2 is 2. 2 into 2 is 4. 4 under Z4, 0. And 2 into 3 is 6. 6 under Z4 is 2. That is here. That means generated by 2 has only 2 elements, 0, 2. Generated by 4 can be written as 4 divides 4. Here, since the remainder is 0, that means we get only one element, that is 0. We call this one as a trivial ideal, and the first one is what? Proper ideal. Let me check whether the condition holds good or not. Which one? M is contained in N. N is contained in what? R. Clearly, I1 is contained in I2 and I2 is contained in I3. Therefore, this is here, okay, and this I3, the set containing what? Only 0 element. Therefore, I2 is said to be the maximal ideal, and we know that every maximal is ideal is what? Prime ideal. Now I will take Z8, that means integer modulo 8. Here we see 8 elements. 8 elements. Sometimes we denote it by 0 bar, 1 bar, 2 bar, 7 bar. That means they are the elements. 0 bar, 1 bar, 2 bar, 7 bar. They are the elements of what? Integer modulo 8. Okay. Now let me form the ideals of integer modulo 8. We have to ignore the first one, that is 0 divides 8, that means generated by 0. We get the set containing only one element, that is 0. We have to ignore it. Let me start from the first element. 1 divides 8 can be written as generated by 1. That means multiples of 1 is same as Z8. Multiples of 2 divides 8. That means generated by 2. Generated by 2 means multiples of 2. See that all the elements should be the member of Z8. 2 into 0, 0, 2 into 1, 2, 2 into 2, 4, 2 into 3, 6, and 2 into 3, 6, 2 into 4, 8. 8 is not at all a member of what? Z8. Therefore, you have to ignore it. Next ideal I denoted by I3. 4 divides 8. That means generated by 4. What we get? Only 2 elements, 0, 4. Last one, 8 by 8, 8 divides 8 means generated by 8. Since the remainder is 0, we get only one element, that is the trivial ideal, the set containing identity element. Here also what we observe? Here we observe that I2 is there in I1, I3 is there in I2, and I4 is there in what? I3 as well as I2. Let me recall. Here what we observe? I2 is I2 is in I1, I3 is in I2, and I4 is in I3 as well as in I2 as well as in I1. Clearly, I2 is a maximal ideal, and we know that every maximal ideal is what? Prime ideal. Therefore, I2 is a maximal ideal as well as the prime ideal of integer modulo 8. Now I'll take the another example, Z12, that means integer modulo 12. Here we observe 12 elements. 12 elements. The first element is 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and so on up to 11 bar. Whenever I indicates the 0 bar, 1 bar, 2 bar, 3 bar, and so on, that indicates they are the elements of integer modulo. They are the elements of what? Integer modulo 12. If you take the ideals of Z12, we get like this. The ideals 1 divides 12 means generated by 1, that is here. 2 divides 12 means generated by 2. The set is here. The elements are 0, 2, 4, 6, 8, 10. Now, 3 divides 12, we get this set. 4 divides 12, that means generated 5, 4. The elements are here. 6 divides 12, that means generated by 6. The elements are the set containing 0, 6. And finally, 12 divides 12, that indicates generated by 12. Since the remainder is 0, we get singleton set, that is set containing the additive identity, that is 0. We call this one as trivial ideal. Here, I2 in this example, I2 and I3 are both maximal. Since both are maximal, therefore they are prime ideals. Next one, Z23. Since 23 is a prime number, we know that if P is a prime number, then it is a field. If it is a field, it has only two ideals. The first ideal generated by 1, the second ideal generated by 23. Okay, since it is a field, every field has two ideals. The first ideal is generated by 1 and the second ideal is generated by 23. Now, one more example, integer modulo 101. Again, 101 is a prime. We know that every prime, if P is prime, then ZP is a field. Since if it is a field, it has two ideals. The first ideal generated by 1. The second ideal generated by the last one, that is 101. Since the remainder is 0, therefore we get only one element inside the set, that is 0. Therefore, I1 and I2 are the only maximal ideals and they are said to be the prime ideals. Now we'll take one more example. Generated by 5, generated by 7 are maximal ideals Also they are prime ideals. Let me check. Generated by 5 means multiples of 5, 0 plus or minus 5, plus or minus 10, plus or minus 50. Generated by 7 means 0 plus or minus 7, plus or minus 12 and so on. What we observe in this example is first one, m is not equal to r. Very clear. M is not equal to r because generated by 5 is not equal to set of integers because 1 is not there, 2 is not there, 3 is not there. Therefore, clearly m is not equal to r. Now, I'll take one element from the first set that is generated by 5. Let me take 15. 15 belongs to 5. That means generated by 5. And 15 can be written as 3 into 5. What we observe, 3 does not belongs to what? Generated by 5 set, and I denote this one by yes. 3 does not belongs to yes, and 5 belongs to what? Yes. What will show? This will show that, this result shows us clearly it is a prime ideal. Similarly, if I take 21, 21 can be written as 3 into 7. Here, 7 is not a member of yes, but 7 is a member of yes. That means the second one. Let me take here, I denote the first set by S1 and second set by S2. With respect to generated by 7, S2. With respect to generated by 5, I take it as what? S1. So these two examples shows that they are maximal ideals as well as what? Prime ideals. Thank you. In the next class, I'll take a few more examples. Okay. Have a nice evening.